The ultimate space odyssey. In 1977, NASA launched two of the most ambitious and daring space probes in human history, Voyager 1 and Voyager 2. Their mission? To explore the vast outer reaches of our solar system and, if they survived, to venture beyond into interstellar space. What started as a 5-year mission to study Jupiter and Saturn turned into a nearly 5-decade-long odyssey, one that is still ongoing today. At the time of their launch, humanity's understanding of the outer planets was limited to ground-based telescope observations and sparse data from the earlier Pioneer missions. Voyager 1 and 2 represented a bold leap forward in space exploration, carrying an array of sophisticated scientific instruments designed to unlock the secrets of the cosmos. Each spacecraft was equipped with cameras, magnetometers, plasma detectors, and cosmic ray sensors, all aimed at providing an unprecedented look at the solar system's outermost realms. But these missions were not without challenges. The vast distances between the planets meant that the probes would have to survive in deep space for years, enduring extreme temperatures, intense radiation, and the ever-present threat of micrometeoroid impacts. To achieve this, NASA engineers built the Voyagers with an extraordinary level of redundancy and durability. Their power source, radioisotope thermoelectric generators, RTGs, ensured a steady supply of electricity even as the probes traveled billions of kilometers from the Sun. Despite these hurdles, the Voyagers exceeded every expectation. As they journeyed from planet to planet, they beamed back some of the most breathtaking images ever captured, transforming our understanding of the gas giants and their moons. The data they collected reshaped planetary science, revealing active volcanoes on Io, a possible subsurface ocean on Europa, the intricate rings of Saturn, the tilted magnetic field of Uranus, and the ferocious winds of Neptune. But the significance of the Voyager mission extends beyond scientific discovery. These twin spacecraft embody the best of humanity: our relentless curiosity, our insatiable desire to explore, and our ability to build technology that endures beyond its intended purpose. They are time capsules, carrying the golden record, a message of peace and culture designed to introduce Earth to any potential extraterrestrial civilizations that may one day find them. Now, as both probes continue their lonely voyage beyond the influence of our Sun, we stand in awe of their legacy. They are more than just machines. They are symbols of our collective ambition, a testament to what we can achieve when we dare to reach for the stars. Join us as we embark on a journey through time and space, retracing the path of the Voyager probes and uncovering the cosmic secrets they have revealed along the way. The Grand Tour, a once-in-a-lifetime opportunity. Key timing of Voyager's launch was no accident. In the late 1970s, a rare planetary alignment occurred, a once-in-176-year event that allowed the probes to slingshot from one planet to another using gravity assists, significantly extending their range and capabilities. This gave NASA a golden opportunity to explore Jupiter, Saturn, Uranus, and Neptune in a single mission with minimal course corrections. Gravity assists, also known as gravitational slingshots, are a crucial technique in space exploration. By carefully timing the probe's flybys, NASA could use the immense gravitational pull of each planet to accelerate Voyager 1 and 2 without expending additional fuel. This technique not only extended their journey, but also allowed them to reach speeds previously unattainable by conventional propulsion methods. With each planetary encounter, the probes gained velocity, propelling them farther into the depths of space. The Grand Tour was a concept first proposed in the 1960s, when scientists realized that the unique planetary alignment of the late 1970s presented an unprecedented chance for exploration. The alignment, occurring only once every 176 years, meant that a spacecraft could visit multiple planets with relatively minor trajectory adjustments. The concept was ambitious, requiring meticulous planning and precise execution. However, funding was a significant hurdle. The original Grand Tour proposal included multiple spacecraft dedicated to different planetary targets, but budget constraints forced NASA to condense the mission into just 2 probes, Voyager 1 and 2. The U.S. Congress was hesitant to approve funding for an extended mission, so NASA engineers had to ensure that the probes were designed to last well beyond their primary objectives. To achieve this, they built the spacecraft with redundant systems, radiation-hardened components, and long-lasting power supplies. Each Voyager probe was equipped with a radioisotope thermoelectric generator, RTG, which converts heat from the decay of plutonium-238 into electricity. This power source was crucial, as solar panels would have been ineffective in the dim outer reaches of the solar system. The RTGs provided a steady, albeit slowly diminishing, source of power, ensuring that the probes could continue transmitting data for decades. Even today, over 40 years later, the RTGs still provide enough energy to keep essential systems operational. The journey of the Voyagers was not without risk. The vast distances involved meant that communication delays could stretch to hours, making real-time adjustments impossible. NASA had to rely on pre-programmed commands and sophisticated onboard computers to execute complex maneuvers. The spacecraft also had to survive the harsh conditions of deep space, including extreme cold, intense radiation, and potential collisions with micrometeoroids. Engineers accounted for these challenges by designing the Voyagers with hardened electronics, protective shielding, and redundant control systems. When Voyager 1 and 2 launched in 1977, few could have predicted just how successful they would become. As they embarked on their grand tour, they provided humanity with its first detailed views of the outer planets, revealing stunning landscapes, dynamic weather systems, and unexpected geological activity. The images and data they transmitted back to Earth revolutionized our understanding of the solar system and paved the way for future exploration. More than 4 decades later, both probes remain operational, sending back data from the very edge of our solar system and beyond. Their longevity is a testament to the ingenuity of the scientists and engineers who built them. As they continue their lonely journey through interstellar space, they serve as silent ambassadors of human curiosity and determination. The Grand Tour was not just a scientific mission. It was a bold statement about humanity's place in the cosmos. It demonstrated that, given the right circumstances, we can overcome immense challenges and push the boundaries of what is possible. Voyager 1 and 2 are more than just machines. They are a testament to our desire to explore, to understand, and to reach beyond our world. And so, with gravity as their guide and the stars as their destination, the Voyagers pressed onward, carrying with them the hopes and dreams of a species eager to discover what lies beyond. Jupiter, the first destination. After 2 years of travel, Voyager 1 reached Jupiter in March 1979, with Voyager 2 following in July. While Pioneer 10 had given humanity its first close-up look at the gas giant, Voyager's cameras provided detailed images of the planet's turbulent atmosphere. swirling storms, and iconic Great Red Spot, a storm larger than Earth that has raged for centuries. Voyager's high-resolution images revealed a dynamic and ever-changing atmosphere, filled with colorful cloud bands, immense lightning storms, and deep convective activity. Scientists were able to measure the planet's powerful magnetic field, which is 20,000 times stronger than Earth's. The probes also detected immense radiation belts surrounding Jupiter, highlighting the extreme environment that any future missions to the planet would have to withstand. Perhaps the most shocking discovery came from one of Jupiter's moons, Io. Before Voyager, scientists expected Io to resemble our moon, a dead, cratered world. Instead, they found an alien landscape covered in active volcanoes. One of these volcanoes, Loki Patera, was spewing lava hundreds of kilometers into space, making Io the most volcanically active body in the solar system. The immense tidal forces exerted by Jupiter's gravity, along with the gravitational pull of Europa and Ganymede, create internal friction that melts Io's interior, driving its relentless volcanic activity. The discovery of Io's volcanic nature fundamentally changed our understanding of celestial mechanics, showing that tidal heating could be a significant source of geological activity. This mechanism is now a key consideration in the study of exoplanets and their potential for sustaining geologic and atmospheric processes. Another major surprise came from Europa, another of Jupiter's moons. Voyager's images revealed an icy world with mysterious surface fractures. Scientists theorized that beneath Europa's frozen crust lay a vast subsurface ocean, a tantalizing possibility for extraterrestrial life. Unlike Io, Europa's surface was relatively smooth, with only a few impact craters, suggesting a young and dynamic environment where ice continuously reshapes the landscape. The implications of this discovery were profound. If Europa harbored an ocean beneath its icy shell, it could potentially sustain microbial life, making it one of the most promising candidates for astrobiological studies in our solar system. This revelation laid the groundwork for future missions, such as the upcoming Europa Clipper, which aims to further explore this enigmatic moon and search for signs of habitability. Beyond Io and Europa, Voyager's exploration of Jupiter's other moons brought additional surprises. Ganymede, the largest moon in the solar system, was revealed to have a complex geological history, with both heavily cratered and relatively smooth regions. The probe also detected a magnetic field around Ganymede, making it the only known moon to generate one, likely due to a liquid iron core. Callisto, another massive Jovian moon, displayed a heavily cratered surface, suggesting it has remained largely unchanged for billions of years, providing scientists with a preserved record of the early solar system. Voyager's encounter with Jupiter was also crucial in refining our understanding of the planet's rings. While Saturn is known for its bright and extensive rings, Jupiter was revealed to have a thin and faint ring system composed mostly of dark, microscopic particles. Scientists hypothesized that these rings were formed by dust ejected from small inner moons due to micrometeoroid impacts. The Voyager flybys of Jupiter were nothing short of revolutionary. They provided data that reshaped planetary science, deepened our understanding of atmospheric dynamics, magnetic fields, and moon formation, and set the stage for future exploration. The images and data collected not only captivated scientists, but also captured the imagination of the public, inspiring a new generation of space enthusiasts. With their observations of Jupiter complete, the Voyagers continued their journey deeper into the outer solar system. Their next target was the breathtakingly beautiful and enigmatic planet Saturn, where even more astonishing discoveries awaited. Saturn, the jewel of the solar system. In November 1980, Voyager 1 arrived at Saturn, and Voyager 2 followed in August 1981. While Saturn's iconic rings had been observed for centuries, Voyager's flybys revealed intricate details never seen before, including complex ring structures and spokes that defied explanation. The rings themselves turned out to be far more dynamic than previously thought, consisting of countless icy particles ranging in size from tiny dust grains to massive chunks as large as mountains. The discovery of spokes within the rings, dark radial features that seemed to appear and disappear unpredictably, left scientists puzzled. These spoke-like structures, later determined to be caused by interactions with Saturn's magnetic field, challenged prior theories of planetary ring dynamics. But the most significant discovery was Titan, Saturn's largest moon. Voyager's instruments detected a thick nitrogen-rich atmosphere, something no other moon in the solar system had. Titan's dense haze prevented direct surface imaging, but scientists speculated that it might have lakes or even seas of liquid hydrocarbons. This finding would later inspire the Cassini-Huygens mission, which confirmed the presence of lakes of methane and ethane on Titan's surface. Voyager's encounters with Saturn also provided the first detailed images of its smaller moons, each with its own unique characteristics. Mimas, often compared to the Death Star due to its massive Herschel crater, showcased a heavily cratered landscape, suggesting an ancient surface. Meanwhile, Enceladus, one of the brightest objects in the solar system, reflected nearly all sunlight that struck its surface. The probe's data hinted at possible geological activity on Enceladus, a suspicion later confirmed when Cassini discovered towering plumes of water vapor erupting from its south pole. Evidence of a global subsurface ocean that could harbor life. Another key discovery was the structure of Saturn's magnetosphere, a vast region dominated by the planet's magnetic field. Voyager measured intense radiation belts, second only to Jupiter's, and found that Saturn's magnetic field is uniquely aligned with its rotational axis, a feature not observed on any other planet. This alignment continues to puzzle scientists today, as it contradicts existing models of planetary magnetism. Voyager 2's flyby of Saturn provided an additional surprise: the detection of a faint outer ring, later named the E-ring. This ring, composed primarily of ice particles, was found to be replenished by Enceladus's geysers, marking the first observed link between a planet's rings and the activity of its moons. The Voyager mission's observations of Saturn transformed our understanding of the gas giant and laid the groundwork for future missions. The discoveries made during these flybys raised new questions about planetary formation, moon interactions, and the potential habitability of icy worlds. These findings were instrumental in shaping the objectives of the Cassini-Huygens mission, which would later revolutionize our knowledge of Saturn and its moons. Voyager's encounter with Saturn was not just a triumph of exploration, it was a reminder of how much remained unknown. As the spacecraft left Saturn's domain, they embarked on a journey to the next great frontier, Uranus and Neptune, two ice giants that had never before been visited by a spacecraft. Uranus, the tipped giant. 5 years after Saturn, Voyager 2 became the first, and still the only spacecraft, to visit Uranus in January 1986. Unlike the gas giants, Uranus appeared as a featureless blue-green ball with few atmospheric details. But Voyager made a groundbreaking discovery. Uranus's magnetic field was severely tilted, unlike any other planet, suggesting a past collision with a massive object. Voyager 2 also detected a faint ring system and discovered 10 new moons, adding to our understanding of this enigmatic ice giant. The discovery of Uranus's tilted magnetic field was one of the most puzzling findings of the mission. Unlike Earth's magnetic field, which is closely aligned with its rotational axis, Uranus's magnetic field is tilted by nearly 60 degrees from its axis of rotation. This means that as the planet spins, its magnetic field wobbles in an unusual corkscrew-like motion. Scientists theorize that this extreme tilt was the result of a massive collision with an Earth-sized object billions of years ago, which also likely caused Uranus to rotate on its side, a unique feature among the planets in our solar system. Voyager 2's instruments also found that Uranus's magnetic field is highly asymmetric, meaning that the field strength varies dramatically between the planet's northern and southern hemispheres. The spacecraft's flyby also revealed that Uranus's rings were much darker and fainter than Saturn's, making them difficult to detect from Earth. Before Voyager, only 5 rings had been observed, but the probe's instruments confirmed the presence of 11 rings in total. The thin and dusty nature of these rings suggested that they were relatively young, possibly formed from the remnants of moons that had been shattered by past collisions. Another major finding was the unexpected dynamism of Uranus's atmosphere. Although it appeared relatively featureless in visible light, Voyager 2's infrared sensors detected strong winds and subtle cloud formations, indicating that Uranus was more active than previously thought. Despite being the coldest planet in the solar system, with temperatures plunging to -224 degrees Celsius, -371 degrees Fahrenheit, Uranus still exhibited complex weather patterns, hinting at unknown internal processes driving its atmospheric activity. The probe discovered 10 new moons, bringing the total count to 27. Among them, Miranda stood out as one of the strangest bodies in the solar system. This small moon had a bizarre, patchwork-like surface, covered in cliffs, valleys, and grooves that suggested a history of intense geological activity. Voyager 2's visit to Uranus was brief, lasting only a few hours, but the data it collected revolutionized our understanding of this distant and mysterious world. The findings from Uranus raised more questions than they answered, paving the way for future missions to explore the ice giants in greater detail. Neptune, the last stop. In 1989, Voyager 2 made its final planetary encounter, Neptune. Unlike Uranus, Neptune revealed a dynamic atmosphere with the fastest winds in the solar system, reaching speeds of 2,400 kilometers per hour, 1,500 miles per hour. Voyager discovered the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, and provided stunning images of Neptune's largest moon, Triton. Neptune's atmosphere turned out to be far more active than anticipated, with bands of clouds moving at different speeds and altitudes. The Great Dark Spot, a swirling anticyclonic storm, was one of the most striking features seen on the planet. But what made it even more fascinating was its transient nature. When the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared entirely, suggesting that Neptune's storm systems evolve much more rapidly than those of Jupiter. Voyager 2 also provided the first close-up look at Neptune's faint ring system. Unlike the bright, well-defined rings of Saturn, Neptune's rings were composed of dark, dusty material, making them difficult to detect from Earth. The The spacecraft revealed that the rings were clumpy and contained bright arcs, leading scientists to believe that gravitational interactions with Neptune's small moons were helping to maintain their structure. Perhaps the most astonishing discovery was Triton, Neptune's largest moon. Voyager's images showed a world with a frozen, pinkish surface covered in nitrogen ice. But what truly shocked scientists were the active geysers spewing nitrogen gas up to 8 kilometers, 5 miles, into space. These eruptions suggested that Triton, despite its frigid temperatures, had an internal heat source, possibly caused by tidal interactions with Neptune. Another remarkable aspect of Triton was its retrograde orbit. It moves in the opposite direction of Neptune's rotation. This unusual motion led scientists to believe that Triton was not originally part of Neptune's moon system, but was instead a captured object, likely originating from the Kuiper Belt. This made Triton one of the most intriguing targets for future exploration, as it could provide insights into the early solar system. With its final planetary encounter complete, Voyager 2, like its twin, set course for interstellar space. As it moved beyond Neptune's influence, the probe continued to send back valuable data about the outer reaches of the solar system, crossing the heliopause in 2018 and entering interstellar space. Even decades after its last planetary flyby, Voyager 2 remains one of humanity's greatest scientific achievements, a testament to the power of curiosity and exploration. The journey of the Voyager probes is far from over. As they continue their silent voyage through the cosmos, they serve as a reminder of what humanity can accomplish when we dare to push beyond the limits of the known universe. Beyond the solar system, into the unknown. After completing their planetary missions, the Voyager probes embarked on their most ambitious journey yet, leaving the solar system. To do so, they had to pass through the heliosphere, a vast bubble of charged particles created by the sun's solar wind. This region acts as a protective shield, separating our solar system from the interstellar medium. Voyager's crossing into interstellar space was not a sudden event, but a gradual transition through several distinct regions. The first significant milestone was the termination shock, where the solar wind slows abruptly as it begins to interact with interstellar particles. Beyond this point, the probes entered the heliosheath, a turbulent region where the solar wind and interstellar medium mix. Eventually, the probes reached the heliopause, the true boundary of the solar system, where the outward pressure of the solar wind is finally overtaken by the incoming interstellar wind. In 2012, Voyager 1 became the first human-made object to enter interstellar space, followed by Voyager 2 in 2018. These milestones marked humanity's first steps into the vast unknown beyond our sun's influence. However, crossing into interstellar space did not mean an immediate escape from the sun's effects. The probes continued to detect the sun's influence in the form of weak magnetic fields and occasional bursts of charged particles traveling from the heliosphere. This data has given scientists an unprecedented look at how our solar system interacts with the broader galaxy. As the Voyagers ventured further, their instruments continued to send back invaluable data about the interstellar medium, measuring cosmic rays, magnetic fields, and plasma waves. These observations have provided scientists with insights into the nature of deep space, revealing a more complex and dynamic environment than previously thought. For example, Voyager 1 detected unexpected pressure waves in interstellar space, hinting at the interactions between the sun's influence and the broader galaxy. These findings suggest that the boundary between our solar system and interstellar space is not static, but constantly shifting due to changes in solar activity. One of the key discoveries made by the Voyagers is the realization that the heliopause is not a smooth boundary, but rather a fluctuating, turbulent region. As our Sun undergoes its 11-year solar cycle, the heliosphere expands and contracts, causing changes in the interactions between solar and interstellar particles. The data collected has helped scientists refine their understanding of how stars interact with their galactic surroundings and how the solar wind shapes our cosmic neighborhood. Despite their incredible achievements, the Voyagers face an inevitable fate. Their power sources are slowly running out, and one by one, their instruments are being shut down to conserve energy. NASA estimates that by the mid-2030s, both probes will fall silent, drifting through the galaxy as relics of humanity's first foray into the interstellar void. Even after they stop transmitting, they will continue traveling indefinitely, crossing vast distances of the Milky Way. Yet, their journey will continue in another way. The golden records they carry, containing sounds, music, and messages from Earth, serve as an interstellar time capsule, offering a glimpse of our civilization to any future finders. These records were carefully curated to include greetings in 55 languages, music from various cultures, and images that depict life on Earth. They provide a message of peace and curiosity, encapsulating the essence of humanity in the hopes that one day, intelligent extraterrestrial life might discover them. Should an advanced extraterrestrial species come across one of the probes thousands or even millions of years from now, they will hear our voices, our music, and our attempts to reach out across the stars. The Golden Records stand as humanity's message to the universe, a declaration that we once existed and sought to understand our place among the stars. The Voyager mission is a testament to human ingenuity, perseverance, and the insatiable curiosity that drives exploration. It reminds us that even as our technology fades, our desire to push beyond the boundaries of the known universe remains eternal. The mission has expanded our understanding of space in ways never imagined, proving that even a mission originally planned to last 5 years can leave a legacy spanning generations. As the probes drift through the cosmos, they carry with them the spirit of discovery, a symbol of our small but bold presence in the vast expanse of space. Their journey will continue indefinitely, passing distant stars and eventually leaving the solar system far behind. In about 40,000 years, Voyager 1 will come within 1.6 light-years of the star Gliese 445, and in 296,000 years, 2 will pass near Sirius, the brightest star in our night sky. Though they will not be operational by then, they will remain as silent wanderers, carrying their precious cargo across the galaxy. Voyager's success has paved the way for future interstellar exploration. Missions like the Breakthrough Starshot initiative aim to send small, high-speed spacecraft to nearby star systems, taking inspiration from Voyager's pioneering journey. The lessons learned from the Voyager's extended mission have informed how we design long-duration space probes, ensuring that humanity's reach into the cosmos continues to expand. Even as NASA prepares for new deep space missions, the story of Voyager remains unparalleled. It is a mission that began in an era before personal computers and the internet, yet continues to push the boundaries of human knowledge today. The Voyagers have outlasted their creators, their designers, and even some of the institutions that built them, proving that exploration is not just about technology, It is about the enduring human spirit. As long as we continue to explore, to question, and to dream, the legacy of the Voyager mission will live on. The spacecraft themselves may one day cease to function, but their impact will never fade. They are a beacon of human curiosity, a symbol of what is possible when we dare to venture into the unknown. So, as we look up at the night sky, let us remember that out there, in the cold and silent void, two tiny spacecraft continue their endless journey, pushing ever farther, carrying our hopes and dreams into eternity. Before their cameras were turned off to conserve power, Voyager 1 captured one final, unforgettable image: the pale blue dot. Taken from 6 billion kilometers, 3.7 billion miles, away, this image shows Earth as a tiny speck of light suspended in the vastness of space. Astronomer Carl Sagan's famous words about this image still resonate today. Look again at that dot. That's here. That's home. That's us. This image serves as a humbling reminder of our place in the cosmos, a mere speck in an infinite void. It highlights the fragility of our world and underscores the importance of unity and preservation. The pale blue dot became more than just a photograph. It became a profound philosophical statement about humanity's existence, our interconnectedness, and the need to care for our only home. Beyond their scientific achievements, the Voyagers carry a message for any extraterrestrial civilizations that may one day find them. Each probe carries the golden record, a time capsule of Earth's sights, sounds, and languages, meant to tell the story of humanity to the cosmos. The golden records include greetings in 55 languages, music from different cultures, the sounds of nature, and images showcasing the diversity of life on Earth. It is a hopeful attempt to communicate across time and space, encapsulating the essence of who we are. The significance of these records goes beyond the possibility of alien contact. They represent a gesture of optimism, a declaration that, despite our conflicts and limitations, humanity aspires to reach beyond its own world. They remind us that we are part of something greater, part of a vast and complex universe that we are only beginning to understand. As the Voyager probes continue their journey beyond the solar system, they become silent ambassadors of a civilization that dared to dream beyond its world. They are now interstellar travelers, destined to drift through the galaxy long after humanity has evolved, changed, or even ceased to exist. If they are ever found, they will tell the story of a species that once looked up at the stars and longed to explore them. Even as their power diminishes, their impact remains undiminished. The data they have collected has rewritten our textbooks, reshaped our understanding of the solar system, and inspired generations of scientists, engineers, and dreamers. The Voyager mission is proof of what human ingenuity and perseverance can achieve. It stands as a testament to the power of exploration and the boundless nature of human curiosity. Though their signals will one day fade, their legacy will endure. The Voyagers will continue their cosmic journey for millions of years, perhaps outlasting Earth itself. And as long as their story is told, they will remain symbols of our unyielding desire to seek, to learn, and to reach beyond the horizon. Their voyage is a poetic reminder that humanity, despite its imperfections, has always dared to dream. We have looked up at the stars and wondered what lies beyond, and we have built machines to answer that question. The Voyager mission embodies our curiosity, our resilience, and our desire to reach for the infinite. As we look up at the night sky, we are reminded that the spirit of Voyager lives on, not just in the spacecraft themselves, but in the unyielding human desire to explore the unknown. The Voyagers may be silent, but their message resonates louder than ever. The universe is vast, and our journey has only just begun. Thank you for joining us on this incredible odyssey through time and space. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more explorations of the cosmos. See you in the next adventure.